Suddenly, a star's explosive death sends its superheated gas ripping through space at hundreds of miles per second. And in faraway galaxies, we can take images of invisible jets of energy screaming out from one of the most mysterious objects, a supermassive black hole. All because of high-tech telescopes.
The telescope has changed the way we as a species think about ourselves.
With a new telescope, you're always going to find something new because you always add to your ability to see more.
These breathtaking images are only possible because extraordinary telescopes like these are staring out night after night across the globe and in space. Over the past 4 centuries, revolutions in technology have transformed this groundbreaking instrument. So where did it all begin? The journey starts with one man and 2 pieces of glass. It is the summer of 1609. Mathematics professor Galileo Galilei is building his own version of an extraordinary new invention. It is the telescope, a name that means far-seeing in ancient Greek. The invention has spread like wildfire across Europe from a small town in Holland. Spectacle makers working on the most precise glass lenses of the day discovered that 2 different types of lenses held at just the right distance produce a surprising optical effect. They act like a magnifying glass for distant objects. This is the birth of the telescope. Galileo immediately sees the potential of the invention.
Galileo is a practical mathematician. That's his trade. He designs instruments, he teaches the use of these instruments, and these instruments are often used for warfare.
Galileo works out how to increase the magnifying power of the telescope to 8 times what our naked eyes can see. And he hits on a military use for it.
And it would be particularly advantageous if you could see the enemy before he can see you.
The Venetian military buys this new device as a spyglass for spotting enemy ships. But then, Galileo turns his telescope from the Earth to the sky and starts a revolution.
By turning the telescope to the heavens, Galileo enters a whole new regime of practice there, where this instrument can be used to discover things we didn't know before about the world.
All astronomers knew of the heavens before Galileo was what they could see with the naked eye, the stars and the moon. But today, even amateur astronomers can see much, much more. Alexandra Hall spends her nights gazing up at the night sky from her backyard.
I never get bored of looking at the night sky above our heads. It's like 2,000 diamonds sprinkled across black velvet. And then the moon arises. And watching the moon go through its phases, I mean, it looks different every time you look at it.
To the naked eye, 5 stars sometimes appear brighter than the rest, and watched over the course of nights, they seem to move against the backdrop of the other stars.
And they don't just stay in the same place like all the rest of the stars. They move around. Sometimes they're visible, sometimes they're not.
Each of these bright stars is a planet, a name that simply means wanderer in Greek. Venus, the evening star, skims the horizon at sunset. Mars glows red. Jupiter and Saturn outshine everything around them. We now know that these wandering stars are actually other worlds, like the Earth, planets as we understand them today. But in Galileo's time, everyone believes they are just stars. There is only one world in the universe, our Earth, and it sits at the very center of everything. The sun appears to circle the Earth during the day, and over the long course of the night, the moon and stars also appear to rotate across the heavens, circling the Earth in giant orbits.
When you stand outside, even just for a few hours at night, you suddenly notice that all the stars, and the planets and the moon, everything is wheeling around your head. It's like you're at the center of things. Really quite a powerful feeling.
But Galileo is about to show that this is just a feeling. He starts to shake the known world order when he looks at the moon. The belief in his day was that all the heavenly bodies were flawless.
In the old cosmology, the moon was a heavenly body and therefore perfect.
But looking across 250,000 miles of space, Galileo sees something very different from the smooth sphere he expects. He sees instead a moon scarred with craters and valleys.
It must have been an extraordinary moment for Galileo to peer with his little itty-bitty crummy telescope at the moon and see craters, mountain ridges, valleys. He saw for the first time geographical terrain on another astronomical object.
This means our Earth is not unique in the cosmos.
These patches that you see are mountains. So the moon isn't smooth, it's like the Earth.
But this is just the beginning. Next, Galileo turns his telescope on Jupiter, one of the wandering stars. He sees it as no one has ever seen it before. This is an exact computer reconstruction of what Jupiter looked like through Galileo's telescope. Calibrated on Galileo's actual lenses, it shows what a challenge he faced. A replica of his telescope reveals how hard it is to get a still image.
Well, when I actually got Jupiter in the telescope, it was really difficult to focus because the lens quality is not very good compared to the lenses that we would get today.
To the naked eye, Jupiter looks like a bright star, a spot of light. Seen through Galileo's telescope, all other stars remain as spots of light. But Jupiter suddenly appears as a much larger round disk. This blurry, shaky view of Jupiter is a revelation. Galileo comes to an extraordinary conclusion. Jupiter must be a sphere, another world, a planet as we understand it today. And around it are even more surprises.
Picture yourself, you've just glued a little piece of glass on the front of a long tube, and to your utter surprise, you see 2 or 3 or maybe even 4 stars next to Jupiter, like little ducklings following a duck.
Night after night, Galileo notes the changing position of these new stars.
Imagine your surprise. Why should stars be following Jupiter? And of course, Galileo learned only after a week or 2 of watching those little ducklings following their mother that those, in fact, were moons orbiting Jupiter.
Galileo knows he has something spectacular on his hands. He publishes his findings in a book called The Starry Messenger.
It is the most explosive scientific book ever written. Its impact was immediate. Galileo became a superstar overnight.
But the biggest revelation is yet to come. Galileo is recording something that will change our view of the universe forever. He observes the planet Venus changing shape and size over a period of months. As Galileo watches, Venus transforms week after week from a large crescent to a small round disk. Then shadows creep again across the planet, returning it to a large crescent. To Galileo, the pattern of shadows he sees on Venus can only mean one thing. Venus is going around the sun. But the belief at the time was that everything circled the Earth. Earth is no longer the center of the cosmos.
And so it said to us, wow, we're not at the center of the universe anymore.
These very simple observations literally rocked the foundations of the world. No longer is the Earth the center of the universe. The sun is the center of the universe, despite what our ordinary senses tell us.
But these discoveries famously bring Galileo into direct conflict with the Roman Catholic Church. The Church taught that God placed mankind on Earth at the very center of creation.
Defending a sun-centered universe, Galileo was actually challenging the authority of the Church. He was contradicting what was considered as the legitimate interpretation of the Bible, and the Church couldn't tolerate this.
But what Galileo saw is the solar system we understand today.
The discoveries that Galileo made, they changed the world forever. The world of science, the relationship between science and religion, and the universe forever.
This is the universe Galileo helps reveal. Planets and their moons orbiting the sun. Telescopes today now reveal this solar system in detail that Galileo could only dream of. Explosions on the surface of the sun, the power of 1 billion megatons of TNT. Features in the Great Red Spot on Jupiter, a vast stormy vortex large enough to swallow 3 Earths. On Jupiter's moon, Io, we can watch volcanoes spew ash and gas high into space. On Mars, a canyon 5 times deeper than the Grand Canyon. And a volcano 3 times higher than Everest. On the surface of Venus, beneath roiling clouds of sulfuric acid, mountains rise from the rocky surface. And circling the sun at the very perimeters of our solar system, dwarf planets made of rock and ice. But one planet remains an enduring mystery for even the most advanced telescopes. Saturn and its enigmatic rings. Galileo was the first to see that this planet was different from the rest. For him, the strange features he observed looked like ears. He presumed they were moons. Later astronomers saw them as a vast flat ring encircling the planet. Then, one man discovered that this ring was in fact made up of several concentric rings. That man was astronomer Giovanni Cassini. Now, a mission named after him is investigating why Saturn has rings at all and what they're made of. NASA's Cassini mission.
3, 2, 1, and liftoff of the Cassini spacecraft on a 1-billion-mile trek to Saturn.
In the nose cone of this rocket is the space probe, Cassini. Ahead is a 2 billion-mile journey to the planet Saturn. On board the probe are sophisticated telescopes. They will investigate Saturn's mysterious rings by traveling as close to them as possible.
Good solid rocket booster separation. First stage
item 152.
As Cassini heads for Saturn, the furthest planet in Galileo's solar system, it uses the massive gravitational pull of Jupiter as a boost to slingshot it out millions of miles towards its destination.
In the world of telescopes, Cassini has some of the fastest moving telescopes in the solar system, going by at Jupiter at something like 70,000 miles per hour.
Even at such tremendous speeds, the journey still takes 7 years. But finally, Cassini approaches Saturn. 934 million miles from Earth. It dives through Saturn's outer rings to enter orbit around the planet. These are some of the images Cassini takes of the rings. They may look solid, but they are made up of billions of chunks of ice and rock, ranging in size from a grain of sand to the size of a house. And they are spread over hundreds of thousands of miles. But where is all this stuff coming from? Cassini's telescopes reveal that the inner rings are made up of material blasted off the surfaces of Saturn's moons by meteorites. But the furthest visible ring from Saturn is still a mystery. This image taken by Cassini shows that unlike the innermost rings, the outermost ring is a ghostly mist of microscopic particles. Astronomers suspect that the icy moon Enceladus could be where the mist is coming from. But until now, no one has been able to work out how. Then, Cassini's telescopes see something never observed before. Vast plumes of vapor streaming from fissures in the surface of Enceladus.
These plumes go up hundreds of kilometers. That's pretty exciting to find erupting out of an icy moon.
Could these plumes be the source of the outer ring? To find out, Cassini's telescopes do something extraordinary. They fly through the plumes and taste the vapor with onboard detectors.
That's a spectacular thing to be able to do, to be able to tap the interior of an icy satellite.
Back at Mission Control, astronomers analyze the data streaming in. The vapor pouring out of Enceladus is made up of ice, salt, and ammonia. It is exactly the same material as the outer ring. It can only mean one thing. Enceladus's plumes are the source of the misty ring. This is a major discovery. Cassini's space-borne telescopes are solving the mystery of Saturn's rings that has plagued astronomers for centuries. Telescopes today are journeying deeper into space and searching further to discover secrets that Galileo could never have imagined. But to capture pristine images like these, telescopes had to undergo a dramatic evolution. Back in the 1650s, the first step in this evolution was going to great lengths, quite literally.
Telescopes became very long, 15, 20 feet.
The problem with early telescopes was fuzzy images. The reason? The shape of the lens. As NASA astrophysicist Kim Weaver demonstrates, when a strongly curved lens bends or refracts beams of light, the light doesn't all come to a single point.
First of all, the different beams of light don't line up, and so the image that you get with this lens would be really fuzzy. Also, some of the light has its colors split out, and that distorts the image.
The only way to minimize the blurriness and the rainbow colors is to use thinner lenses with a shallower curve. Because the light comes to a focus further from the lens, refracting telescopes get longer and get greater magnification. 17th century astronomers make ever thinner lenses and space them further apart.
By about 1660, telescopes had magnified 50 or 100 times, and those lengths increased and increased and increased.
This is the first space race. On the quest to see ever further, telescopes reach absurd proportions, up to 150 feet in length, half the length of a football field. These unwieldy telescopes are better, but astronomers want to see even more detail, and these telescopes don't eliminate the rainbow colors altogether. Then, one of science's greatest minds sets out to solve the problem: Isaac Newton. He takes a look at light itself.
Newton found that white light was in fact composed of all these different colors, the colors of the rainbow.
As white light passes through a glass prism, it bends or refracts, breaking up into the colors of the rainbow. This was the root of the astronomers' problems.
Now, a lens is a kind of a prism, if you like. Once the light hits the lens and passes through it, it's broken up into its colors. So Newton says, well, we'll abandon refracting telescopes completely. There's no future in this. Just forget them. I'm going to design a telescope which has mirrors as the primary components instead of lenses.
Newton will use mirrors in his new telescope. He believes he can do this because when mirrors are curved, they bring light to a focus, just like a lens.
I'm using this lens right now to focus the light from the sun behind me. And if I hold it just right to a point on the card, oh my goodness, it's catching on fire. That was smoking.
Next up, the curved mirror.
And you can see as I bring it closer to the focal point of the mirror, it actually begins to burn the paper again.
But there's one critical difference between a mirror and a lens. The light bounces off the mirror's surface. It doesn't pass through it, so there are no rainbow colors. Newton creates a tiny telescope only 6 inches long. He makes a curved mirror only 1.5 inches across and inserts it into the base of the tube. Light from the heavens passes down the tube, reflects off the curved mirror, then reflects off a second flat mirror, and is focused by an eyepiece. This small reflecting telescope works just as well as a 4-foot telescope that uses lenses. Isaac Newton, in creating the first reflector, eradicates rainbow colors, a problem that has plagued telescopes since the time of Galileo. Today, telescopes stare out from observatories across the world and in space. They are expanding our view of the cosmos, capturing light that has been traveling across our universe for billions of years. The clarity is so exceptional that these real images continue to amaze and inspire us. All these telescopes rely on large mirrors with the perfect shape. Making them is a feat of precision engineering. Deep below the football field of the University of Arizona is a high-tech mirror lab, where glass blocks are melted in giant furnaces at over 2,000 degrees Fahrenheit, the temperature of volcanic lava. The hot liquid is spun into super smooth curved dishes. The 20-ton discs of cooled glass are then ground to within fractions of a human hair to make the precise shape. It is only when a thin film of aluminum is applied, only 100 nanometers thick, that the glass dishes become mirrors, like those of the large binocular telescope in Arizona. At 28 feet wide, these mirrors are 64,000 times the size of Isaac Newton's first mirror. And they can collect light from stars billions of light years away. In Isaac Newton's day, making large mirrors exactly the right shape is far too difficult. It will be a century after Newton before a new pioneer picks up his revolutionary design and transforms it. That man is musician and amateur astronomer William Herschel. Herschel has great ambitions. He wants to use a larger version of Newton's reflector to see further into space than anyone before.
Herschel is a musician. He's not an astronomer. He's a clarinet player, he's an impresario, he's a composer. But his real passion isn't music, it's astronomy.
Herschel wants to look anew at the night sky. He wants to look beyond the planets to the stars, and to see the very faintest stars invisible to other telescopes of the day. Herschel needs big mirrors.
He builds telescopes that are bigger than other people's because he realizes that the wider his aperture, the more light he can collect, the further he can see into space.
Making large curved mirrors, though, is still a major technical challenge in Herschel's day. Glass mirrors have not yet been invented. Mirrors are still made of metal. So working in his basement, Herschel casts discs of a metal called speculum, a special mixture of molten tin and copper. These will become his mirrors.
We don't know what the neighbors thought of this mad fiddler burning the entire road down.
Casting the metal discs is just the first step. To become mirrors, the cooled flat discs need a shiny curved surface. Herschel painstakingly grinds and polishes the metal discs by hand into the precise shape needed to form an image.
This is the reflecting mirror, the most precious component in the telescope, made in metal by William Herschel himself, made by hand. He was like a craftsman, making something which required manual skill as well as intellectual effort.
This telescope, over 200 years ago, makes a revolutionary discovery.
Or perhaps a comet.
In 1781, Herschel peers night after night into the heavens. At his side, his sister Carolyn.
Following Delta Tauri.
She records all their observations and will become a prominent astronomer herself.
Her observations were critical.
She was one of his true secret weapons.
Then, on March 13th, Herschel sees an object through his telescope that they have never recorded before. A very faint star that seems to move against the backdrop of the other stars. This wandering star is a brand new planet, Uranus.
The planets have been identified since the dawn of written astronomy. And then suddenly you have this clarinet player, you know, with homemade telescopes in his back garden. He discovers another one. The thing is utterly astonishing.
Uranus, with its own set of rings, is the size of 63 Earths. But no one has identified it before because it is barely visible with the naked eye. 1,900 million miles from the Sun, it is twice as far from the Sun as Saturn, until then the furthest known planet. Overnight, Herschel doubles the size of the solar system. The discovery sparks a frenzied hunt for planets. It is a quest that the world's most sophisticated telescopes continue to this day. The sun is setting on Mauna Kea, Hawaii. The giant dome of the Keck Observatory opens. Its 33-foot wide mirror turns toward the heavens. Jeff Marcy is one of the world's foremost planet hunters. He is using the Keck telescope to hunt for planets in solar systems beyond our own.
Well, when you look up into the night sky, you see all the thousands of twinkling lights. Those are stars like our sun.
Planet hunters like Marcy think that many of these stars could have their very own planets. But finding them is another question.
Your mission as a planet hunter is to find that needle in the haystack.
Telescopes only made a breakthrough as recently as 1995. They recorded a perfectly ordinary star wobbling minutely. There was some gravitational pull on the star, evidence of a planet they couldn't see orbiting around it. Exoplanet 51 Pegasi b.
The discovery of the first planet around a normal star, around 51 Pegasi, was an extremely profound moment for humanity. We now know, as a species, that there are other worlds out there.
Since then, teams of astronomers across the world have found evidence for more than 400 other exoplanets. But most of the planets discovered so far are gas giants the size of Jupiter, orbiting far too close to their suns to support life. And a planet that can support life is what the planet hunters are really after.
What we'd love to know is whether there are other Earths, habitable worlds out there, whether they are lukewarm with liquid water, having the vibrancy, the conditions suitable for life, and perhaps even intelligent life.
Looking for small rocky planets like Earth is a whole new ballgame. Cue a brand new NASA space telescope called Kepler.
And liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler's 3-year mission is to find planets the size of our Earth orbiting other stars.
Vehicle's now going supersonic.
I think Kepler is going to go down in the history books as one of the greatest telescopes ever in the history of humanity.
Kepler's mission is to collect light from a field of 100,000 stars inside our Milky Way, looking for clues to other worlds. As the dust cover falls away, it begins measuring the starlight.
All that happens is you watch the star, and Earth happens to orbit in front of the star. It blocks a tiny fraction of the starlight on its way, and when it blocks that light, the star dims a tiny amount.
Kepler has already discovered several new exoplanets. It hasn't found an Earth-like planet yet, but astronomers believe it is only a matter of time.
I believe in the next few years we will have the first detections of Earth-like planets, places that you might indeed want to call home.
Though Kepler is looking at 100,000 stars, this is only a tiny patch of the sky. There are hundreds of billions more stars out there to search.
The hunt for exoplanets requires that we look at hundreds of thousands of stars.
So planet hunter David Charbonneau uses more down-to-earth technology.
The revolution has been to use Hubble telescopes to study the closest stars.
Using small robotic telescopes, he scans 2,000 stars that are far less bright than our own sun. This makes it easier to spot a small planet passing in front of it. And he has discovered a planet only 2.7 times the size of our Earth, a super-Earth. Importantly, it appears to be covered in water and have an atmosphere. At 400 degrees Fahrenheit, it is still too hot to inhabit, but it's a tantalizing glimpse of what is out there.
If we can succeed in finding habitable worlds, then that would have implications far beyond mere astronomy.
In a bid to find habitable planets, the professional astronomers are getting a little bit of help on the side.
Amateur astronomers are central to our understanding of planets orbiting other stars. The amateur astronomers are stationed, of course, all over the world. They have telescopes which are certainly large enough to conduct the survey.
Ron Bissinger is one such astronomer. He is following in the footsteps of William Herschel and his discovery of Uranus.
When I come up here every night and open that thing up, fire up the telescope, fire up the computer, I know the target star I'm going to look at. Everything is mine. That's my world alone. I may, for that night, be the only human being looking at that star.
He has a telescope advanced enough to help out the professionals.
Professional observatories cannot spend the time staring at one star night after night after night, but we can.
He too waits for the telltale dimming of a star's light, just one star at a time.
to find a world out there that no one's ever known of or seen or detected before from your own backyard. A person who is not a career scientist. I don't know of any other scientific endeavor where somebody like me or so many other amateurs can do that kind of thing.
Bissinger's patience has paid off. He has already discovered several large exoplanets of his own, though all are too close to their suns to support life. Like all known exoplanets, they orbit stars within our galaxy. We know today that this is a vast collection of stars in which our Sun, Earth, and solar system also reside. But just over 200 years ago, we didn't even know we lived in a galaxy. Discovering this just by looking at the stars would be a great challenge. In 1781, William Herschel is the man who takes the challenge on. To do it, he just needs a bigger telescope. He builds a reflector 20 feet long. With this, he is able to see more stars than any other telescope on Earth, and he observes one part of the night sky in particular. The strip of stars we call the Milky Way. This will be Herschel's key to the shape of our galaxy. On a clear night, the Milky Way is a majestic spectacle. A brilliant band of starlight arcing overhead. To the ancients, it looked like milk had been poured across the sky, and it's why the Greeks first called it the Galaxias Kuklos, or Milky Circle. It's from this we get our word galaxy. It fascinates astronomers to this day.
The Milky Way stretches across the sky from horizon to horizon. It's like a big band that goes all the way around us. And so from here on Earth, it's kind of like we're sitting on the hub of a wheel, and the Milky Way is a big tire all the way around us.
Looking through his telescope, Galileo was the first to discover that the Milky Way is made up of stars. But no one knows it is a galaxy. They don't even really know what its shape is. Finding this out now becomes Herschel's obsession.
What is the actual shape of the Milky Way? We're in the middle of it, presumably. What would it look like from the outside?
He gazes tirelessly at the heavens night after night, mapping the positions of stars.
Herschel is nothing if not passionate. He's a natural obsessive. But good for him, he does something extraordinary with this obsession.
Herschel maps the distribution of all the stars he can see in a great circle that cuts through the Milky Way.
He introduced into astronomy the technique of star counts and just counting how many stars can I see.
One direction you see very few stars, in another direction you see zillions of stars. And so he plots this distribution and comes up with a view of the Milky Way.
The survey takes over a year of precise recording. Herschel finally produces a map called the grindstone because of its shape. For the first time, Herschel sees that the Milky Way is more than just a strip of stars in the sky. It is a vast disk of stars, and Herschel believes this is the whole cosmos.
When Herschel made his map of the Milky Way galaxy, to him he was making a map of the entire universe.
The edges of this star disk are the edges of Herschel's universe. Inside it lies our solar system, our sun and our Earth. The amazing thing is that over 200 years ago, Herschel almost got it right. The most powerful telescopes on Earth and in space now revealed that Earth and our solar system lie in a spiral arm in the suburbs of our galaxy, dwarfed within a giant disk of 200 billion stars spinning together around a bright central bulge that hides a supermassive black hole. The Milky Way is so large that it would take 100,000 years traveling at the speed of light that's 670 million miles per hour, to cross from one edge to the other. Now, a new telescope is about to see what more it can find out about our Milky Way. The Herschel Space Observatory. Bill Latter is a key member of the Herschel team.
Herschel will map the entire Milky Way galaxy in terms of how stars are formed, how stars die, and how the galaxy is put together.
After years of careful preparation, the finely tuned telescope is about to launch.
Launch is a violent thing. There's no other way to describe it. We light this candle, it shakes, we throw the thing out into space, and we only can hope that it all holds together.
1 million miles above Earth, the largest mirror ever launched into space is looking beyond visible light to wavelengths our eyes cannot even see, the far infrared. This means it can measure tiny fluctuations in temperature and see right through clouds of dust to give us the clearest images of the Milky Way ever.
The results were astonishing. What we're able to see with the Herschel Space Observatory are right into the cradles of newborn stars. We see something very different than we would with our eyes. If we looked at the same region in visible light, it would be full of stars. But here, in the infrared, we're seeing dust and gas that really make up the majority of material in our galaxy, and it's where stars form.
No other telescope is able to see the Milky Way in this detail. Stars in these regions of our Milky Way were invisible to William Herschel. Yet over 200 years ago, he can see more in the night sky than anyone before him. And as he maps the stars through his telescope, one great mystery remains. Thousands of strange objects that astronomers can't explain. They call them nebulae, Latin for clouds.
There are fuzzy patches of light that you can see in the sky. They kind of look like pieces of the Milky Way that have been detached, and a couple of them you can actually just see with the naked eye. But through a telescope, there are thousands of them, and they have all kinds of different patterns and shapes and sizes. They're quite beautiful and quite mysterious. One of my favorites is the Andromeda Nebula, which you can actually see with the naked eye. And through a telescope, I can find it here. It's really mysterious. You just see this glowing light that gets brighter and brighter towards the middle. It's like, what is that?
Herschel makes a catalog of these mysterious objects, counting and classifying over 2,300 nebulae. But even with his giant telescopes, Herschel can't tell what they are or where they are.
There were little smudges that you could see in the best telescopes of the day. Those smudges were thought to be nebulae, clouds of gas, but people began wondering how far away those smudges were.
The mystery of the nebulae will continue to perplex astronomers for decades. 60 years later, at Birr Castle, Ireland, the eccentric Lord Rosse builds the largest telescope in the world. He wants to finally crack the enigma of the nebulae. 6-story walls support a tube 60 feet long, and the mirror is the height of a man.
He's a natural engineer, and if you see the great Leviathan of Parsonstown, as it's called, this great 6-foot aperture telescope, it's a vast machine.
Lord Rosse points the telescope at the nebulae. He sketches what he sees. For the first time, the fuzzy clouds begin to come into focus. Inside some of them, Rosse can see stars and spiraling structures. But there is a problem. Rosse's telescope can only move up and down, and the mirror tarnishes easily. the giant telescope falls into disrepair. It will take 80 years, a great revolution in technology, and a telescope bigger than Galileo ever imagined, high on a mountain peak, before the mystery is finally solved. This great telescope on Mount Wilson, California, will reveal that the spiral nebulae, first sketched by Ross, are in fact separate galaxies beyond our own. The universe will be blown wide open.
It completely revolutionized our idea of the scale of the universe. No longer were we just confined to the Milky Way.
Our galaxy, the Milky Way, will no longer be the only galaxy in the cosmos. It will become just one of hundreds of billions of galaxies spinning within an inconceivably vast universe.
The introduction of telescopes to astronomy opened up an entirely new window on the universe.
The race will continue to build bigger and bigger.
Our technology has reached a point where we can build gigantic ground-based telescopes. We can launch huge space-based telescopes and see the most distant things in the universe.
The telescope is pushing forward the frontiers of our universe. So what will colliding galaxies billions of light years away tell us about our own Milky Way? And right at the limits of the cosmos, what will the afterglow of the Big Bang tell us about how our universe began?
Every time you try and explore a new part of the universe, we have these great discoveries and these great surprises.
Most surprising of all, telescopes will reveal that right now we can only see 5% of the universe.
Only a few percent of the total matter and energy content of the universe consists of things that we can see.
So what is the rest of the universe made of?
In many ways, we're at the beginning of our quest of discovery. We're learning about the major part of the universe we didn't even know existed 10 years ago.
Telescopes will point to an elusive and powerful force that is shaping the fate of our universe. Dark energy.
I think dark energy is the most mysterious thing we've ever discovered.
Telescopes are on the brink of a new era of discovery and exploration.
It's such an exciting future to think about all of the discoveries yet to come.
We are uncovering a universe we are only just beginning to understand, as telescopes that are bigger and more sophisticated than ever continue the hunt for the edge of space.
In the universe, it's important to know your nearest neighbors. But how much do we really know about our corner of the Milky Way? In just the last few years, scientists have uncovered incredible secrets lurking in our own backyard. New moons, new planets, and new mysteries.
It's like there was a house in your neighborhood that you never knew was there.
Meet new neighbors who are just passing through.
There are planets that are wandering the galaxy aimlessly without a place to call home.
And old friends whose days are numbered.
It's conceivable that Betelgeuse will go supernova tonight.
Join us for a tour of the neighborhood we're only now getting to know. This is Our Place in the Milky Way. This isn't your neighborhood. Neither is this, or any of these. And it isn't even this. Looked at from a wider perspective, your neighborhood is a big cloud of gas. Astronomers say the solar system is moving through the local interstellar cloud, also called the local fluff, because of its low density and irregular shape.
The gases are mainly hydrogen and some helium. There are trace amounts of heavier atoms like carbon and oxygen and nitrogen that are just floating around the interstellar medium. We know that the heavier atoms in the interstellar medium are left over from previous explosions of stars as supernovae.
The local fluff is 30 light years long, about 180 trillion miles. It's inside a larger chimney-shaped gas cloud called the local bubble, also the remnant of an ancient supernova. The bubble is 300 light years long and lies in the inner edge of one of the spiral arms of the Milky Way. And that's our neighborhood. At least we think it is.
Our exact position in the Milky Way galaxy relative to the arms actually isn't known. The structure of the galaxy is not known in any real detail. Some people think there are 2 major arms, some people think there are 4 major arms. It's hard for us to determine the exact structure of our Milky Way, where all the arms are and so on, because it's kind of like a mouse being inside a maze. You don't get the big picture.
In almost any Earth neighborhood, you can determine your location very precisely.
Turn left in 30 feet.
But when you're dealing with something as big as the Milky Way, GPS isn't an option.
The galaxy is, 100,000 light years across.
Even exploring our local neighborhood involves a lot of uncertainty. But if we did have a galactic positioning system, it would probably locate us about midway between the top and bottom of the Milky Way, and about midway between the galaxy's outer edge and inner core.
Our solar system is about 26,000 light years away from the center of our galaxy.
According to one hypothesis, we have a very exclusive location.
There's one idea that only stars in a certain range of distances from the center of our galaxy are in the so-called galactic habitable zone, that is, able to have life on planets surrounding those stars.
It is just the right place with a star of the right temperature and a planet at the right distance for there to be a lot of liquid water on the surface where the chemistry of life began and evolved into us.
The overall range of the galactic habitable zone extends from about 13,000 to 35,000 light years from the center of the Milky Way. The main part, where we are, ranges from 20,000 to 29,000 light years from the core. Inside the zone, old neighborhoods have been destroyed to make a place we can call home.
Depending upon how you look at things, our local neighborhood, our local solar system is actually a relatively safe place compared to what seems to be going on if you look at the universe in the large. In the early history of our solar system, it was a much more violent place, and the material that formed the sun and the planets was still sorting itself out. There were all sorts of collisions and violent things happening that gave rise to this nice, calm, or relatively calm place that we have today.
We think that the earliest stars formed out of hydrogen and helium alone, but that over time, the stars work as these processors that create the heavier elements. This is important because when those stars eventually die and explode, these supernovae, or stellar death explosions, seed the galaxy and the material around it with heavier elements.
So, for example, the carbon in our cells, the oxygen that we breathe, the calcium in our bones, the iron in our red blood cells. all those are heavy elements.
We know that the sun is at least a second or third generation star because there are planets around it. There are things made of iron and carbon and other heavier elements.
But the processes that led to life on Earth don't seem to exist outside the zone. Closer to the edge of the galaxy, fewer massive stars have exploded, producing fewer heavy elements.
Further out in the galaxy, you don't have as many atoms like carbon, nitrogen, oxygen, the atoms that are so important for the chemistry of life. So the habitable zone of the galaxy cuts off at a distance where you just won't have the heavier atoms to make life.
If the outer galaxy is a bad neighborhood, the inner area is even worse. Gravity from massive gas giant planets could tear us apart. And there are other dangers the closer you get to the galactic core.
Back in the times of Copernicus, we thought that we were the center of our universe. And even as we started to learn more about the heavens, eventually we still thought that we were the center of a galaxy. Now that we know even more, though, it actually turns out that we're lucky we're not in the center of the galaxy.
At the center of the Milky Way, sucking matter and even light into it, is Sagittarius A star, a black hole nearly 14 million miles across, with a mass 3.7 million times that of our sun.
Yeah, the galactic center has a black hole in it. It gives off a lot of radiation. It's enough to fry life as we know it. So you can't be too close to that. Then there are other regions in the galaxy that are also probably not so great for life because there's just so much radiation from nearby really hot O-type stars.
O-type stars are giants. They're hotter than the sun, 10 to 50 times as massive, and throw out titanic amounts of ultraviolet radiation. With these stars, you don't worry about sunburn, but extinction.
It's probably not easy to survive in an environment where you're in a tight cluster with a lot of O-type stars.
O-type giants can destroy planets before they form.
The radiation from these stars is so strong that it actually sweeps the material away from these newly forming would-be planetary systems and rips it out of the orbit of their stars.
If you want proof, look at the Rosette Nebula. It's 5,200 light-years away, far outside the local bubble. But it shows what O-type giants could do to our neighborhood. A 2008 study by the University of Arizona of 1,000 stars in the nebula found star after star had been made barren by being too close to a blue giant. So what's a safe distance from the radiation of an O-type giant?
Well, if you ask me, you can never be too far away from a giant. If you're life like us here on Earth, we're used to our fairly tame sun. You want to be probably at least tens of light years away, maybe more than that. Really, just don't get too close.
Like a city between a desert and an ocean, our corner of the galaxy thrives between two different, inhospitable regions. With the elements of life and without the threat of intense radiation, it seems like our neighborhood is literally the only place to live. But is our place in the Milky Way really so exclusive?
The idea of the galactic habitable zone is that if you're too close to the center of the galaxy, there's all these crazy things going on and it tends to kill off life. To be honest, I'm personally skeptical of the idea because I think that life can happen in all sorts of environments, or at the very least, we don't know. So we should be open-minded. It's possible that our kind of life can only live in this galactic habitable zone, but elsewhere there could be other kinds of life that we would call extremophiles. On the other hand, they would call us extremophiles.
One thing is certain. In our neighborhood, we have a sun that, unlike a blue giant, protects us from danger and destruction in ways that we're still learning about. That protection may be invisible, but if we lose the sun's protection, our neighborhood could be doomed. Our place in the Milky Way seems pretty peaceful because, like a lot of communities, we don't give much thought to the 24/7 security systems that keep the bad stuff away. Many cities on the edges of rivers or oceans have dams and levees to protect them from floods. If the dams and levees fail, disaster. We've got threats and defenses on a galactic scale, too.
Space is filled with radiation, known as cosmic rays. Cosmic rays are bad for us in the same sense that nuclear radiation here on Earth would be bad for us. Because high-energy radiation tends to disassociate carbon bonds, which is what we're made of. What you're really doing is damaging your DNA, and there's a potential there that you could start to have mutations based off of that.
Some mutations can help a species survive or lead to extinction.
There's no evidence that cosmic radiation has really negatively impacted Earth in the past, but it's nothing that you want to play around with.
Our neighborhood's prime defense against cosmic rays? Magnetism.
We have this zone of protection in our neighborhood. Of course, the Earth has a magnetic field due to how things move around in the core of the Earth. The Sun also has a powerful magnetic field, and it also has the solar wind. These phenomena actually generate ways of protecting us from things that come from outside the solar system.
The Sun's magnetic field is twisted by the solar wind. Streams of charged protons and electrons that shoot out of the Sun at 1,000,000 miles an hour.
Then the particles that live in the solar system between the planets actually stretch the lines of the magnetic field around in complicated patterns.
The solar wind carries the magnetic field more than 3 times farther out than the orbit of Neptune. But 9 billion miles away, at a place called the heliopause, the solar wind runs out of steam and slows to almost nothing. As it slows, it twists the Sun's magnetic field into a barrier against cosmic rays from interstellar space. This is the heliosheath.
If it wasn't for the heliosheath, these cosmic rays would actually pour into our solar system all the time. The heliosheath acts as a kind of shark cage for these incoming cosmic rays that might otherwise influence our planet.
Some do come through, but they don't come through as strongly as they would without that protection.
It used to be thought that the heliosheath was a rather elegant barrier made of flowing curtains of magnetic force. But recently, enter Voyager 1 and Voyager 2, probes sent out from Earth in 1977. In the early 21st century, these disco-era devices sent back information indicating that the Sun's magnetic field lines don't flow smoothly together. They break up and reform into violent magnetic froth, and each bubble in that froth is 100 million miles wide.
We used to think that it was a smooth, nice barrier between them, but in fact it's a roiling place with all sorts of bubbles and patterns. I think there's always been people who think the universe is more elegant than it is, and people who think it's more violent than it is, and we're always surprised one way or the other. The truth is that some aspects of the universe are quite elegant, and in other aspects it's quite a mess.
Where are the elegant areas of our galactic neighborhood, and where are the rough parts? It can be hard to tell with all that gas and dust in the cosmos.
It's sort of like looking here. Behind me is Hollywood. There's even a landmark there, the Capitol Records building. You can barely make it out. And even beyond that, there are some hills that are even hazier. It's because there's stuff in the air that blocks the view. The hill itself obscures my ability to look beyond it, and that's kind of like the dust in very dense molecular clouds. When you hit a big wall of a dense molecular cloud filled with dust, you can't see anything.
When we explore our galactic neighborhood, what we see depends on how we look at things.
One of the things we've learned through the history of looking at the sky is that every time you look in a different way, you see new things. And looking at the sky a different way often simply means looking in a different part of the electromagnetic spectrum. As we look up into the sky with our eyes or with the aid of optical telescopes, in the visible part of the spectrum, we see the night sky, and there's a lot to see, but it's only a fraction of what's out there.
Some space telescopes see through cosmic dust with infrared vision, similar to that used by commercial infrared cameras.
I've brought with me this plastic bag, and when I put my hand inside of the bag, you can't see how many fingers I'm holding up. With the infrared camera, you can see the heat coming off my body. So my face, which is warm, is red and white, but my hair, which is cool, shows up as blue. So with the infrared camera, you should be able to make out how many fingers I'm holding up, even though you can't see through this bag. That's how astronomers peer through cosmic dust when they want to see things that are hidden from sight. For example, stars being born are very warm, but they're obscured by dust shells. With infrared, we can see them.
Certain objects are transparent or opaque depending upon the frequency of the light that's trying to get through them. And so, in fact, something that's getting in the way, like a lot of interstellar dust or gas, is getting in the way of what your telescopes can see, are actually invisible in another part of the spectrum. You can see what's behind.
With infrared and a multitude of other wavelengths at our command, we've discovered a lot of neighbors we didn't know we had.
There's a whole array of instrumentation which is exploiting that lesson that if you look in a particular part of the spectrum, you see the sky in a very particular way.
From what we've observed, it looks like some old neighbors might have helped life form on Earth, while some newer neighbors may be planning to wipe us out. As we've explored our place in the Milky Way, we've met a lot of interesting new neighbors. But there are good neighbors and bad ones.
Good neighbors are, for example, objects that are in predictable orbits, moving around, doing their own thing, minding their own business. We can look over and wave to them, but they're not going to do something sudden or dangerous to us. The bad neighbors then would be things that may do something unstable. They may do something that could affect us in a way that we can't predict when it's going to happen. So that might be when a star dies and explodes. Or it might be when something collides and bounces off something else and comes spinning in our direction. So classifying things roughly into good neighbors and bad neighbors is really a classification into predictability and unpredictability, or violence and non-violence, if you like.
Sometimes a good neighbor will bring a moving-in gift. That might have happened to us billions of years ago, as the Earth was still cooling and forming out of recycled material from a recycled sun. We might have received a gift that changed everything.
The early Earth was very hot, and probably any original surface water evaporated away. So we think that quite a bit of the water may have come from either comets or icy asteroids, or both.
One of the theories about how we might have gotten so much water here on Earth is from icy bodies in the outer solar system left over from the formation of the sun and the planets, crashing into our inner solar system where Earth lives and delivers some of that water.
According to one recent theory, about 4 billion years ago, the gravity of gas giants like Jupiter sent icy asteroids slamming into Mars, Earth, and Venus. But only on Earth did the ice penetrate into the mantle. The water softened the Earth and initiated a titanic process of plate tectonics, which led to the emergence of continents and oceans. And what of the life that formed in the oceans? Did organic compounds necessary for life also splash down from space? In rare meteorites called carbonaceous chondrites, scientists have found organic compounds like those that helped form life on Earth. These compounds are similar to what's been collected from many different sources, including Antarctic micrometeorites, interstellar dust, and comet samples acquired by NASA's Stardust mission in 2005.
The origin of life involves a long series of reactions with many different organic molecules being just ones with carbon in them. And it's possible that different circumstances are needed to make the different organic molecules. Some of them might be made here on Earth, but others might be easier to make out in space and then bring them here to Earth on asteroids or comets.
It's possible that without extraterrestrial gifts from our neighbors in space, life on Earth might never have happened. Milky Way neighbors may have helped nurture us, but the Milky Way has things that can kill us as well. With something like this, an orange dwarf named Gliese 710. It's about 60% as massive as the Sun and is currently just 63 light-years from Earth and getting closer.
Gliese 710 appears to be heading pretty much straight toward the solar system.
As an orange dwarf approaches the solar system, it becomes more and more significant. When it's about a light-year away or less, then it becomes very important.
Almost exactly 1 light-year away from Earth is a huge region of icy objects called the Oort cloud.
The Oort cloud objects could turn into comets if they were to come close enough to the Sun, but usually we don't see them at all because they're so far away from the Sun.
Billions of potential comets are waiting for something to give them a gravitational push. Something like Gliese 710.
It'll start intersecting the Oort cloud, or at least gravitationally disturbing it, in something like 1.3 million years.
If Gliese 710 gets close enough, its gravity could turn harmless chunks of ice and dust into rampaging comets launched at us. The results for Earth could be devastating.
At that point, there could be a huge onslaught of comets into the inner solar system that could lead to another mass extinction. We don't know that that'll happen, but it could happen.
Astronomers say there's an 86% chance that Gliese 710 will barrel right through the Oort cloud.
So if the orange ball was like an orange dwarf, like Gliese 710, and the pins were the Oort cloud, this is one thing that could happen.
All right, but here's something else that could happen. There's a 14% chance that Gliese 710 is just going to pass right by outside the Oort cloud, not coming inside it at all.
But even without a direct hit, the effect of the star's gravity could disrupt at least some comets and send them straight for us.
So the star could knock just a few comets toward the inner solar system.
And all it takes is one comet to hit Earth to cause a catastrophe.
We've got more than just Gliese 710 to worry about. There are more than 150 stars close enough to disturb us within the next 2 million years.
The stars in our Milky Way galaxy are all gravitationally bound together. So they're moving in various directions, overall a rotation around the center of our galaxy, but not all the orbits are exactly the same. That means from our perspective, a given star might be going away from us or toward us.
And NASA estimates there are more than 20,000 near-Earth asteroids more than 300 feet across. Like 2005 YU-55, which in November 2011 came closer to the Earth than the Moon. It might come even closer in 200 years. How bad would it be to get hit by a rock like that? Think about Nagasaki at the end of World War II and multiply by 4. As we've searched our corner of the Milky Way for other neighbors, bad and good, we've found some very unexpected things. We now have evidence of stars cold enough to touch and planets straight out of science fiction. Exploring our place in the Milky Way has turned up one surprise after another.
It's like there was a house in your neighborhood that you never knew was there and that you've suddenly discovered, but is just down the block.
Take Alpha Centauri, the brightest star in the constellation Centaurus, and after the Sun, our nearest neighbor star, 4.3 light-years, or 25 trillion miles, away. In the 17th century, astronomers announced that Alpha Centauri was really 2 stars. Then in the 20th century, it turned out to be a triple system.
Alpha Centauri A is very much a Sun-like star, nearly exactly the same mass as our Sun. Alpha Centauri B is a little bit less massive. The third star, Proxima Centauri, is an M-type star. It's a very low-mass star, having perhaps only 12% the mass of our Sun. It's so faint that we can't see it with our unaided eye.
It turns out that other very well-known neighbor stars are also multiple systems. Sirius, just 8.6 light-years away and famed for thousands of years as the brightest single star in the sky, is really a binary star.
Most stars are less massive and smaller than our Sun, and most stars are in binary systems. In both respects, our Sun is a little bit of an exception.
The majority of stars are red dwarfs or brown dwarfs. Red dwarfs make up 70% of the stars not only in our galaxy, but in the universe. And so, even though we orbit our Sun and we tend to think of it as the iconic star, really, the red dwarfs are far more common.
As for the brown dwarfs, these are neighbors we weren't sure existed until the 1990s. They're not quite stars, but they're not planets. Oh, and they're not really brown either.
The brown dwarfs are some of the most mysterious denizens of the solar neighborhood because they're really very, very cold. And they're very dark, and that means that they don't give off a lot of light, and they're very difficult to see.
In 2011, one of NASA's space telescopes, the Wide Field Infrared Survey Explorer, or WISE, found a series of brown dwarfs right in our neighborhood, between 9 and 40 light-years away, with surface temperatures once considered impossible.
One of these brown dwarfs that we found is actually so cool that you could touch it with your hand. It's only 80 degrees Fahrenheit, the same temperature as a really lovely day out here on Earth. And so, who knows what else we'll find? The more we look, the more we see.
Why are stars so many different colors? That's what Anna Kay of Baton Rouge, Louisiana texted to Ask the Universe.
Anna, that's a really interesting question. Basically, stars have slightly different colors because they have different surface temperatures. Cool stars like Betelgeuse look reddish, and they have temperatures of only 6,000 or 7,000 degrees Fahrenheit. The hottest stars like Rigel appear bluish, and they're upwards of 20,000 degrees. Then there are stars like the Sun with temperatures of 10,000 or 11,000 degrees, and they look white. Now, the sun looks yellow when it's setting, but that's because of atmospheric effects. Its true color is white.
There are more than stars out there. We've discovered hundreds of neighboring planets inside and outside the local bubble.
We have discovered a lot of exoplanet candidates through a mission called Kepler that is looking at essentially little eclipses when a planet moves in front of its parent star and then out, and the light dips a little and then goes back up.
It's very difficult to see, analogous to watching for a single light bulb going out on the Vegas Strip. But Kepler is capable of doing these measurements so precisely that it's able to find even planets as small as our own Earth around stars like our Sun.
The first exoplanet we discovered was only about 15 years ago, and it was very much like we were the only house on the block, and we saw the first neighbor putting up their house. And ever since then, the entire neighborhood has grown. You built up communities of other exoplanets out in our local neighborhood.
As far as we know, our nearest planetary neighbor outside the solar system is just down the street, 10.5 light years away, orbiting the orange star Epsilon Eridani.
This planet isn't exactly something that we could go visit and expect to find life. We think that this planet is more equivalent to a planet like Jupiter in our solar system, a big ball of gas, which, as we understand it anyway, isn't a great place to look for life.
A little farther out, about 200 light years, is another surprise. A planet that looks like something out of a Star Wars movie.
Just recently, the Kepler telescope discovered a planet that orbits two suns, and this is a planet called Kepler 16b. So this planet, even though it has similarities to Tatooine, isn't exactly like Luke Skywalker's homeworld. It's actually a planet that's icy and gassy, more like Saturn than our own Earth. Now, we were never sure prior to this discovery whether you could have a planet that actually has two suns. And so, now that we've found one, we know that these are possible. And that's really interesting because it means that these binary systems are good places to look for planets.
In 2011, astronomers unveiled a new kind of planet in our neighborhood, the homeless.
There have been some indications that there are planets to be found that are not in orbit around their parent star. They started out in orbit around their parent star, but somehow got ejected from their solar system, and now they're wandering the galaxy aimlessly without a place to call home. So one wonders if pretty soon we'll have another new definition that encompasses those bodies that used to be planets and no longer have a parent star.
I think it's still valid to refer to these ejected bodies as planets because planet is the Greek word for wanderer, and they are certainly wandering through deep space.
We've even learned new things about our solar system neighbors. In the summer of 2011, the Hubble Space Telescope took the first pictures of the dwarf planet Pluto's previously unsuspected fourth moon.
Now you might wonder, Pluto's not all that distant. Why did it take us so long to find a fourth moon? Well, it's because it's very, very small, only 10 to 20 miles in diameter. So it's very faint. It reflects only a little bit of the sun's light.
The new moon is probably a frozen, lifeless world, like Pluto itself. So far, all of our newly discovered neighbors have been too hot or too cold to have any possibility of our kind of life. But the search goes on.
So even though we haven't done it yet, we're at this point where our technology has caught up to our needs, and we're actually going to be able to start finding those planets like Earth in the really near future. However, being able to determine whether they would be supportive of life is a much more difficult task.
None of the exoplanets we've discovered in our corner of the Milky Way pose any threat to us. But what about some of the stars out there? Could some of them die and take us with them? Our place in the Milky Way has a lot of pluses. we're right in the zone for life to form. Our closest star protects us from dangerous cosmic rays, and most of our neighbors don't disturb us. But neighborhoods can change. If a fire destroys a nearby home or business, your home could also be damaged. So imagine what might happen when a star goes out of business as a supernova.
That means they'll explode and throw all their innards back out to the galaxy.
Exploding stars created us, most of the heavy elements in the stars around us, and the gas clouds the solar system dwells in. But it's a bad idea to be too close when a dying star explodes.
A supernova explosion is an incredibly powerful explosion. The core of the star bounces out and smashes into the outer layers and blows them out into the galaxy. So what actually happens is that material gets thrown out in a shock wave that, if you're near enough to the shock wave, would be destructive.
If it's 10 light years away or so, then high energy radiation, like from X-rays and gamma rays, can harm us. It can, for example, destroy part of the ozone layer. What happens is the radiation comes in, disrupts nitrogen molecules. The nitrogen atoms then combine with oxygen to form nitric oxide. That nitric oxide, NO, disrupts ozone molecules, O3, and forms nitrogen dioxide, NO2. The nitrogen dioxide can then combine with atomic oxygen, forming more nitric oxide, which then disrupts more ozone, which leads to a snowball effect. So within a few weeks, you can destroy much of the ozone layer, allowing the sun's ultraviolet radiation to come in, and that would then kill life that's on the surface layers of an ocean or in ponds.
That death toll would include the phytoplankton that are the foundation of the marine food chain and provide 50% of the Earth's oxygen. And that would spell doom for most larger forms of life, including us. One candidate for stellar extinction lies outside the local bubble, although it's been a familiar sight for thousands of years. The red supergiant, Betelgeuse. The star, between 500 and 800 light years away and 20 times the mass of the Sun, forms the right shoulder of the constellation Orion.
Betelgeuse is getting near the end of its life.
Between 1996 and 2011, Betelgeuse shrank by 15%. For reasons that are still not understood. The red giant may go supernova in 500,000 years, or it may have already happened.
It's conceivable that Betelgeuse will go supernova tonight, or tomorrow night, or next week. But it's much more likely to become a supernova in 100,000 years or in a few 100,000 years. Given that Betelgeuse is at least a few hundred light years away, it's possible that it's already blown up, and we just don't know it because the light hasn't reached us yet.
The good news is that even if Orion does dislocate its shoulder, Betelgeuse is too far away to harm our neighborhood. But then there's HR 8210, about 150 light years away in the constellation Pegasus. It's not one star, but two. A star and a white dwarf in binary orbit around each other. The white dwarf is about 15% more massive than our Sun. Not at the supernova tipping point, yet.
HR 8210 is this binary system, two stars that are orbiting one another, one of which has actually already died and is a white dwarf. Now, this system has the potential that when the star that's very hot right now starts to go through its death throes and starts to puff up as it dies, it might start to pour material onto that white dwarf. Essentially, these systems are like zombie stars eating their companions.
When that normal star starts to expand, the white dwarf will start stealing material from its companion, becoming more massive. And if it reaches a certain unstable limit, it'll blow up as a Type 1a supernova.
Are we far enough away to avoid being collateral damage when HR 8210 explodes?
If you want to be completely safe from a supernova, you should be at least 100 light years away. 10 light years might be enough, but it might not. It depends on what effect kills you first.
But that won't happen for a really long time. And by then, we will have moved off, and it will have moved off, because everything in the galaxy is really on its way somewhere. So over time that might happen, but at the point that it does, it probably won't be very close to Earth at all anymore.
But don't feel too comfortable. The threat of HR 8210 was only discovered in 2002. How many more potential supernovas are out there? How close are they to us? And how soon will they explode? To possibly make matters worse, some astronomers say that there are a lot more supernovas in our neighborhood's future.
Our solar system orbits our galaxy at a different rate than the spiral arms do. That means eventually we're going to enter a spiral arm. And because there's a lot more massive stars there, some of them will be ending their lives creating supernovae and posing a greater threat to life on Earth.
Still, our place in the Milky Way is secure for tonight, and for at least a few million nights to come. Plenty of time for more exploration and more surprises.
We live in a pretty diverse neighborhood, actually, and things are changing. The galaxy is not a static place, so it's going to be an interesting place to see in a billion years.